Recording is rolling. It is Wednesday, May 8th. That's 9 days until the exam. I have a bunch of challenge questions lined up for you guys today. Of course, we're on this fun schedule. This class I'm recording right now happens to be sixth period is today, right now in front of me. So we have C lunch. So we're going to be here almost an hour. So this recording should go almost an hour. You guys see, right? Might the class will be a little shorter. And then, guys, Friday. That's not tomorrow, but the day after. Oh, okay. Actually, this is for my first 4 classes getting relocated. Okay, so that's okay for the video anyway. All right. So you guys got some paper out or your notebooks, even better for some challenge questions. You guys ready for some challenge questions? Now what I'm gonna do is all these posters that I've been designing over the past few years, a lot of them are correlated to AP. I mean, there's a bunch of extra stuff too, right? But here, I'm gonna use this checklist. All right, so this one right here, scaling. I do want to flash in front of you guys. This is going to show up by the time we get to Unit 3. They like to ask scaling questions. For example, here's the question I'm eventually going to ask you guys. See if we get this today or not. Suppose you're on some planet that has, sometimes the mass of Earth and sometimes the radius of Earth. What's the gravity field of the surface of that planet? Now, that's going to be a scaling question, right? So eventually we'll get to that. But other than that, I want to go approximately the order that we. All right, so that's going to be Unit 3 by the time we get to it. Okay, so you're ready for that one. All right. So here, I got an algebra for you guys. All right, so real simple algebra. Oh, whoops. Let's just throw this over. Got a fraction in parentheses here. All right. So you guys write that one in your notebook. Go ahead and solve that. Somebody tell me, what is x equal to? What is x equal to? 7. Yep. Actually, there's also a secondary answer. So 7 is correct, but there's also another answer that works. No. 1/3. Yeah, there you go. Yeah. So yeah, Steve got 7, Sydney got 1/3. Right. Here's the full process right here. Right. If you graph this, or I guess there's different ways you can make a graph of this, but if you have y equals and somehow figure that in there, this would be a parabola shape, right? And then you could kind of interpret this as like, where does it cross the axis? And parabolas can possibly cross 2 places, right? So here. Okay, so this has a bunch of operations in it. So take the square root of both sides, that square, and immediately splits into 2 possibilities because positive or negative, you get plus or minus. Okay. From there, see, cross multiply the 5, 2 times 5 is 10. Okay. Then see, add this 11 over, boink, looks like that. Okay. And finally, divide both sides by this coefficient 3, boom, 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 boom. Right? So that should be a real softball question right there. Right? So, all right. Next one, let's do some trigonometry. Okay. So okay, you might see, suppose you see some vector. I'll call it how about some general v, like a velocity could be, right? Okay. You want to split that into components. Say, well, how fast is it going across and how fast is it going up? Say you had those Cartesian systems, right? Throw in some angle theta. Okay. Or right, later on, set this up for later. Right? Maybe this will be a double question. Okay. What if you have an incline? You have a block on an incline, and it has some weight. I'll call it mg. And you think, okay, well, I'm gonna find out this in terms of this rotated Cartesian system, which looks about like that. Okay. Can you split this guy into components? All right, boom, boom. Right. So there's a 2-for-1 question here. Okay. And so somebody tell me, what is this leg right here equal to? B cosine theta. Yeah, B cosine theta. Right? If you had numbers, if that V was like 10 meters per second and that angle was 30 degrees, 10 meters per second times cosine 30 degrees, okay, you do something like that. Okay. And what is this like right here? V times sine theta. There you go. Okay. Right. Now, if you ever have a right triangle and there's something about the 2 legs, right? Because the 2 legs have a what kind of relationship with each other? Sine, cosine, or tangent? Tangent. Some to tangent, right? Okay. Like tangent of that angle is opposite over hypotenuse, if you think of it. Okay. How about this block on this incline? Now, the full weight of the block is mg, right? That's Earth point down. You could also do f sub g. That's okay. F sub g. Okay. I'll call it mg. Guys, is this angle here? This angle here is that same angle? Yes. Right. All right. So this component that's actually trying to drive the block down the incline is equal to what? Yeah, mg sine theta, mg sine theta. Right? Okay, because we got another right triangle. I give the hypotenuse. Both of these setups, you guys notice both of them involve right triangles, and I gave you the hypotenuse. Is that? Right? Of course, the physics application is called vector components. And this one right here is equal to what? Mg cosine theta. You guys said, right? Which, if as long as there's nothing else fancy going on, that's also equivalent to the normal force, isn't it? Mg cosine theta. I guess that. Right. So that's that poster. That's gonna pretty much show up later on. I've got a block on an incline poster. It's gonna show up later on too. Okay. Ooh. All right. Here's a fun challenge question. Guys, write on your paper as many measuring tools as you can think of from this class. Let's see who can remember the most. I have a whole list in front of me. Okay. Write down as many measuring tools that you could possibly be asked to use on the AP exam. So we're gonna throw out ammeter and voltmeter. You're not gonna use those. Okay. So no ammeter, no voltmeter, but everything else you can think you can possibly use. Right? You're gonna get an experimental design question. And you're gonna have to say what variables are you gonna measure with what measuring equipment that you've used in this class. All right. Everybody got a list? Okay, so I got a list right here. Let's see how you guys did. You guys ready for this? All right, so I got a meter stick or a ruler for some kind of displacement, right? And different scales, but they're almost interchangeable, right? Meter stick ruler, okay? You could protractor could be an angle in degrees, right? That's possible measuring tool. Okay, you guys got it? Do you guys get a stopwatch to measure time in seconds? Okay. Right now, this next one, motion detector. Yeah. Okay. If you put speed guide on paper, I know that's what we've been using in class. Those little Stonehenge gates and fly something through it, right? If there's an application on the AP exam, then use this one instead. Say motion detector, because that's the term they're going to be looking for, right? Also, if you have to describe how you're setting up the motion detector, guys, does say you have a little Hot Wheels car, can that roll straight towards or straight away from the motion detector, right? It's how you would set it up, okay? And they would be also looking for something like that, right? I know in class we did the gate version of that, but okay, so this is for the AP exam, right? Oh, we need some way to get mass. Triple beam balance works for mass. Digital scale works for mass. Killer, right? Okay. Spring scale could be a force or a weight, right? Force probe. AP likes to use force probe. I mean, we've read so many FRQs in this class. Looked at the. Okay. You guys see force probe all over the place. Okay. Again, ignore these last two because you're not going to be asked about voltmeter and ammeter. Okay. Yeah. What is it's kind of like a spring scale, but you can push with it. So you push, and it says like, oh, I'm pushing with 9 newtons, something like that. Yeah. I guess I just imagine that. Okay. All right. Ooh. How about let's do some prefixes. These may or may not show up. Right. Here. Let's do it this way. Guys, capital T, what does that stand for? Tera is what I'm looking for, right? And that's 10 to the power of what? Let's go 12, right? With 12, like, I think it's a trillion, right? T, tera, trillion, ta. Okay. G, giga, that's 10 to the 9. Is that like a billion, I guess, right? Right. Capital M, mega, 10 to the 6, right? K, kilo, 10 to the 3 is 1,000, right? Lowercase m is a prefix. Milli, yeah, that's 1/1000 something, like 1 millimeter. There could be 1,000 millimeters in a meter. 1,000 milligrams in a gram. Well, not quite. Micro. That's Greek letter mu. In this context, as a prefix, it can be micro, right? Okay. Of course, we're recycling all these letters for other uses too, right? Yeah. So it's 10 to the -6. That's 1 over a million, right? So micro and mega are opposite. Right? N is nano, 10 to the -9. Here, nanotechnology, nanobots, nanometer. Pico, haha, right, which I highly doubt you're going to see, but in case you do. Right, guys, right. Write down the 3 kinematic formulas. Write them down, 3 kinematic formulas. You should probably have these memorized by now. Of course, I mean, you guys, they will give you this page, and it has a version of them up here too. I mean, there's a little bit different forms of these, so go to college, might tell you a little bit different. I taught them one way, AP writes them a little bit different way. Let's see, who knows these 3 kinematic formulas? Yep, I got them. Okay, getting them there. Okay. That looks good, I think. Looks good. All right, you guys getting these 3. All right, you guys know the 3 kinematic formulas. All right. All right, so let's run through these, double check your work, make sure for sure you got them. Right. You got displacement. My term for X would be displacement, not position. Now, AP goes the extra detail of they have final position equals initial position plus, and then they do the rest of this, right? Right. But this could be delta X. So speed times time. Now, if acceleration is 0, isn't that the whole thing? Distance equals speed times time, right? Cruise control on the interstate. Right? If you start from rest, can you bump this term? Just say X is 1/2 AT squared, right? And then if you put it together, if you're starting not from rest and you're accelerating, boom, boom, put that together, you get the whole thing. Okay. Okay. Now notice, guys, which of the 5 kinematic variables does that not mention at all? Final velocity. Yeah, there you go. You found how fast you're going at the end of the interval is not mentioned. Right? Okay. Here's final velocity equals initial velocity plus acceleration times time. So this is speeds as a function of time, right? And isn't that third one speeds as a function of distance? Okay. Or I should say velocity is a function of displacement. Okay. Right. Good. All right. Let's see what else we got on my posters. Ooh. Here we go. Who could tell me? Let's say you go out to this balcony, you start blasting balls off, and you measure how far does it land and how high was the balcony. Right? So you know those. You know this height, and you know where it landed. I want you guys to derive how fast was that ball blasted. What's the blast speed? Got part of it set up for you guys. Maybe that's a nice little hint right there. What is the blast speed? Oh, you know what I should have asked you before this is you guys remember doing you teamed up in friend pairs. One of you guys dropped a ruler, the other caught it as fast as you could. How far it fell told you the time of fall. Right? That's actually embedded in this one. So you have to know that to get this. Right? That's what I'm covering up. You guys, a little more time here. If you get this, that's a real good sign. You know what you're doing. You probably get that from scratch. Hopefully. All right, let's do step by step. Hopefully you got this. We're getting pretty close to the end. Okay. Guys, what's the first step I'm probably covering up right here? I forget for sure. Yeah, I think probably this one. Probably I threw in there, right? Okay. Now, for that to work, here, look, is that my first step? Okay, yeah, that is my first step. Right, guys, for that to be true, what am I implying here is the initial velocity in the vertical direction? 0, right? Doesn't that only work as long as you blast it straight horizontal? Right? Yeah. Now, if you blast it at any other angle, then it becomes much more complicated. Right? Okay. If AP does that, if they like blast it at 30-degree angle, I'm gonna guess they probably ask like a graph question or something like that, but not necessarily solve it. Right? So then let's get time in terms of the drop height. Right? Now that right there is the answer to the ruler question. You dropped a ruler, your friend caught it. Right? What was their reaction time? Boom, boom, boom. As long as you plug in the correct units. Okay. And then substitute that over there. The blast speed is boom, looks like that. Okay. Show hands. How many guys got that? How many guys got that? Ooh, okay. A couple guys. Okay. I think that would be a completely fair free response question. You guys can see that. And see lots of other things too. Huh?
Does it not matter that you inverse?
Right. Because 2h over g, but then I'm dividing. So when you divide by a fraction, you flip the multiply. Do that, right? Yeah. So you could say d divided by square root of 2h on g. You could do that. Right? Or you could say d times square root of g on 2h. Yeah, you do both ways. Right? All right. Let's see what we got next here. Ooh, let's do some graphs, right? We're going to set up lots of graphs, so I may as well set up lots of axes here. I'm about to set up lots of axes, lots of axes, lots of axes. Right, you guys are writing lots of axes in your notes. Boom, boom, boom. Boom, boom, boom. Boom, boom, boom. Right, and you guys know what we're setting up. Right, let's divide this into 3 scenarios. Point, point, point. Okay, so scenario 1, car drives at constant velocity. Okay, let's do distance versus time, or I should say displacement versus time, velocity versus time, acceleration versus time, right? Also throw in some units. Let's go meters and seconds, meters per second, seconds, meters per second squared, and seconds. Okay, so you're on I-95, just driving north, cruise control. What do those 3 graphs look like? The next one we're going to do is, let's say, speed up from rest, and then let's do brake to a stop. Okay, we'll do this. Okay, X, V, A, X, V, A, all versus time. Okay. Any of these graphs, any of these scenarios, you can see. Okay. All right. You guys got driving constant velocity? All right. Actually, before I flash up the answer, I do want to check right around, see. Ooh, okay. Yeah, I think that looks good. Right, almost. Right. Oh, all right. Yeah. Okay, I think you guys got this. You guys got this. That looks pretty good. Pretty good. All right. I think you guys got knocked that one out. All right, so here's this one. I think you guys have thumbnail notes of all these too, right? You look back at your thumbnail notes, right? So see, the car is picking up a position at a constant rate. Right? That constant rate is called velocity. Right? The slope of that graph is the coordinate of that graph. Oh, there's constant velocity. The speedometer needle's just same number over and over, right? No matter how much time spent, which means no acceleration. There's constant velocity. Boom, boom, boom. Right? You guys got that. Okay. All right. How about what if the car starts from rest, slamming the gas pedal and speeding up uniformly? Maybe I'll throw in that word, uniformly. Speed up uniformly from rest. You guys got those graphs? Right, start from rest, speed up uniformly. Okay. Guys, what shape graph did you do for X versus T? Parabola. Right. So this poster, got a little bit different scenario. Say you're dropping a ball from top of a cliff, I'm calling the top of the cliff 0.0, but it's the same set of graphs, isn't it? Right. So yeah, got a parabola for position versus time, a linear relationship for V versus T, right? And the slope represents acceleration in that case, right? And then A versus T would be a constant value for this class. Almost always that'll be the case, right? If it's accelerating, it'll be a uniform acceleration. Okay. So I got that. Oh, see, I said car brakes to a stop. Okay, car brakes to a stop. Go ahead and make those 3 graphs. Car brakes to a stop. Yeah, those are all exactly correct. Yep, that's exactly correct. Okay. Okay. Yeah, I'll do this. That's I got that's on reverse. I got 3 winners so far. Yep, 4 winners. All right, take a look at 4 winners here. 4 winners. 5 winners. Got 5 winners. All right. All right. Okay. So, all right. Actually, maybe I should start with the middle graph. I usually do on these, don't I? Right. So you had some initial velocity, but you go to 0 velocity, right? And you probably do that at a uniform rate, right? So start with that one, okay? Which means you have a negative acceleration, right? If you're driving forward but slowing down, that's a negative acceleration, right? Now x versus t. This one looked like it was pretty tricky. Again, like 5 of you guys got this, okay? So keep in mind the car's going forward. So as time's passing forward, you're still moving forward, right? You're just doing that at a slower and slower rate. So is this a parabola? Yeah, this is a parabola. Where's the vertex? Right, the point that it stops. Ah, that's what that is, right? Notice, like if you broke this into say like 3 intervals, you guys know the first interval goes pretty good distance. The next interval, doesn't go as far. The last interval, now it's rolling to a stop, doesn't go hardly any far at all. It goes a little bit. Okay. You guys got car break to the top. Okay. Right. I have some other graphs in front of me. Let's do these. Okay. If I asked you guys to do these, so let's go back to the cliff. If you throw the ball upward or throw it downward. Now, notice how I have these graphs. I'm defining, oh, I got this picture in the middle. Notice I'm defining down as a positive direction. I'm defining the top of the cliff as 0.0, right? Now, you guys know AP might frame the question exactly like that, or they might turn everything upside down, right? They might say, hey, call the ground 0.0, and then call the top of the cliff like the 100-meter mark, right? Okay, so maybe all these graphs could turn upside down if gravity is negative, right? You could do that too, right? You guys ready to feel that? Right? And possibly throw an intercept on these if, say like this is your first time. Right, see, I have the top of the cliff as 0.0, right? So that's why I started this at the origin. Okay. And then I have gravity as positive. Okay, so I got it. Okay. So you guys ready to field those? Here's one I'm just going to throw up here because we kind of already covered this one. You guys remember this? Right. You guys remember this lab? Right. You held a ruler, your friend caught it. Right. However far the ruler fell, that could tell you something about the reaction time. This is exactly how you solve it. Boom, boom. All right. Starts from rest. Got that. Right. Boom, boom, boom. Right. Now, when you guys actually did this lab, remember to have everything in base SI units. So, guys, suppose this ruler fell 14 centimeters. What number goes in for the height fall? You can plug in 14. No, because that would mean 14 meter sticks, which is like whoa, 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 whoa. How about what number? 0.14 meters. That would correspond to maybe 9.8 meters per second squared. You round it to 10 as a continuum. Right? Right. Got some Newton's laws posters. Guys, what's Newton's first law of motion? Yeah. Yeah. So first law of motion, exactly. I hear you guys saying it. Object to rest will remain at rest. Object to motion will maintain its velocity, which has 2 parts to it. That's speed and also direction motion. Unless an external force is acting on that object. Right? That's also called law of inertia. Right? So if something is ever speeding up or slowing down, right, or going around a curve, right, it might have constant speed, but you're just turning. Right? That would also mean that there's an external force. Okay? Right? Guys, what does Newton's second law of motion say? There you go. F equals ma. I usually like the fraction form myself, right? Because I think it's cause effect, right? So why does something accelerate? Could be speeding up or slowing down. Could be going around a curve. Right? Centripetal. That's okay. Net force acting on a mass. Okay. Notice I'm saying net force. So there could be multiple forces acting on an object. So you have to figure out, okay, well, what if there was, as if it was a single force, right? Okay, got that. What is Newton's third law? There you go. Right. Every action equal and opposite reaction. So if 2 objects are pushing or pulling on each other, here's pushing, here's a pulling. Okay. It's just equal force on each object, opposite directions. Okay. You know you're going to get out of this. Right. Now it's usually like maybe there's a collision or 2 blocks are pushing against each other and say, which force is bigger, right? Is it the big block against the little block, or is the little block on the big block? It's the same force. You guys see plenty of those. Okay. Ooh, right, this next one, I got elevator physics. You're going to see some elevators in some context, right? Possibly an Atwood and say, what's the tension in the string? That also applies to this, right? You know what I did not do on this poster? I think I made a new one in the meantime. is actually derive this. So I like this end result because okay, what is the tension in this cable? Or you could say the normal force reading on the scale, right? It could be M times G plus or minus A or something like that, right? Got a bunch of scenarios going here. I got 6 different scenarios, right? Moving up and slowing down, or moving down faster and faster is both that one, right? At rest or constant velocity, that's both this. And then moving up faster and faster, or moving down slowing to a stop could both be this. Okay. Can you derive that from scratch? Okay, I'll derive it from scratch off screen. You guys derive that from scratch. Right. Start with a free body diagram and then derive that from scratch. Let's see if we get the same thing. So setting up an elevator off screen here. I'll do tension, force, and weight. You can do normal force and weight. That's okay too. Same math. Okay. Let's see. I'm gonna do that. That. Okay. My very last line is tension force equals something, or you could say normal force equals something if you like. You want to do it that way? So all right, so I just finished my derivation. We'll walk around the room, see who's able to derive this from scratch from that free body diagram. Who's able to get that whole process. Aha, yep, that's it. Okay, all right. See, some of you guys still working on it. I think some of you guys got it. All right. Okay. I know for sure Addie got it. Wait, does anybody else think they got it? Okay. Ooh, okay. All right. Apparently this one's kind of tough. All right. So you guys ready to get the answer right here? Get the answer right here. All right. So I'm just going to derive this pink one right here. So tension up, weight down, start from there. Okay. So that's what I got right here. All right. Tension up, weight down. Right. Or if we're standing on a scale, normal force up and weight down. Okay. So here's Newton's second law of motion. Net force equals mass times acceleration. So we got that. Okay. Now guys, what is the net force according to this diagram? Yeah, tension minus weight. Okay, so that's going to substitute in there, isn't that? Like that, right? Now, I'd like to know, what is that tension in that cable? Okay. Or you might get the question, what is your scale reading if you're standing on a bathroom scale inside that elevator? Okay, so I need to solve for that. So I'm going to take that mg, slide that over. Looks like that. Okay. And then if you like, you could factor out the m. And there you go. Just like that. Just like that. Okay. Now, if that's a multiple choice question, do you guys think it might be real handy to have that expression in your back pocket and just pull out and solve it real fast and move on? Right? I think so. Right? If it's a free response question, you think you better show every one of those steps. Because it could be like point, or something like that. You guys think? All right, what do I got next here? Ooh, let's do. I got an Atwood lined up. Classic Atwood. Right. And what I'm covering up are a bunch of expressions related to that Atwood. Let's start with, what is the acceleration? Now, this is all in terms of variables. So let's say I'm holding this pulley in place, massless frictionless pulley. Okay, so okay. So these blocks, I got M1 and M2. Maybe M2 is larger than M1, just like my picture shows, right? There's going to be some acceleration. Now, AP will probably phrase that as, what is the downward acceleration of the large block? That's usually how they say it. Right? You guys go ahead and solve that from scratch. Let's suppose this is a free response question. You want to show all your work, all your steps, how you derived. What is the acceleration for that system? I mean, you know, you're going to see some Atwoods, right? There's no way they couldn't ask you an Atwood question. It's a real classic physics right here. Ooh, all right. Let's see, Addie's got it. Who else has got this? All right, some of you guys got a good start, looks like. Getting there. But if you crack that one, the follow-up question you might be asked is something about the tension in the connecting string. Right? Can you guys figure out that too? Okay. So I'll start setting this up. Right here, just going to show you what you got. Right? You got 4 boxes. It's not exactly a logical sequence, but they're kind of related to each other. Right? So here's Newton's second law of motion. Right? Acceleration is net force on total mass. Right? And there's 2 approaches to answer this question. Like, what's the acceleration? One way is what AP calls a whole systems approach. That's usually what I do with you guys. So I'm saying from the whole systems point of view, these 2 external forces, these 2 weights, are subtracting from each other. One says, let's go clockwise. No, let's go counterclockwise. So you subtract those 2. Right? That's the net force on the whole system. Right? Then, okay, well, how much mass is being moved? How much inertia? Oh, well, that's M1 plus M2. So there's the difference in weight over sum of masses. Right? If you like, you could factor out the G from the top. You don't have to, but you could. Right? So there you go. That's the answer. That second box is the answer. Right? Right. Then if you hit the follow-up question of, hey, what is the tension in the cable? And remember, that tension is always going to be the medium force. It's going to be larger than the small weight, but smaller than the large weight. So you can drive the correct accelerations, right? Right? Small one accelerates up, the large one accelerates down overall. Right? So what is that tension? Well, here's where you want to pick one block or the other. They'll both give the same tension. There's only one tension in that string. Okay? So here's from the point of view of mass 1. Right? Say, if I just have a free body diagram, just focusing on mass 1, got the tension up, the weight down, that's resulting mass times acceleration for that individual block. Hey, is that acceleration? Is that same acceleration? It is, right? And then from the point of view of the large block, here's the weight down, the tension up, they're subtracting. That's going to result in m times a the large block. Right? And I have down as being the positive direction for the large block because it's accelerating down. Is that right? Now it could be you could. Here's the other way of doing this. You could approach this from a micro point of view. You could start with these 2 bottom boxes. If you go to college, there's a chance that maybe your college instructor might possibly prefer to do it that way and say solve the system of equations, right? And you can get all the same answers. You get now that method you get acceleration and tension 2 for 1. Okay. You guys want to do a numerical example? Let's do a numerical example. Okay. Let's suppose I can make something up. Say I got 7 kilograms versus 1 kilogram. Right. 7 versus 1. Right. Let's figure out both those questions. What's the acceleration and what's the tension? All right, you guys solve it. I'll solve it. See what we get here. Okay, oops. Yeah, that's about right. All right. All right. So I'm getting 7.5 meters per second squared, and the tension is 17.5 newtons. Right. You guys getting that too? You guys getting that? How many of you guys got that? Got that? Right. Getting there? All right. But walk you guys through that. Right. So it's here. So step by step, it's the same thing we did in terms of variables, but now we just got numbers. Right. Right. I'm starting with whole systems point of view. The 70 newtons versus 10 newtons. Well, those are subtracting. Okay. So I got 60 Newton net force to say clockwise or counterclockwise. That's acting on 7 plus 1 is 8 kilograms. Divide that out, get 7.5 meters per second squared. Okay? Notice the acceleration is bounded somewhere between 0 and pure free fall, right? Which will always be the case for these outwards. Right? Okay. Now, how do you get the internal tension, right? So pick one of these blocks. Say I pick this one, right? Say, well, it's got a weight down and it's got this tension force up. So I have to take the difference between those two, right? Accidentally set this up backwards. Oops. Yeah, I was running out of paper space, so I kind of squeezed this into a space too small, right? But ideally, I would set up F equals ma, net force equals mass times acceleration for that particular block, right? If this was a free response question, they might be looking for that step, right? And you plug in values. So net force is, say, I should have said 70 minus tension. That's what I should have said, okay? But I compensated for that. I slapped in a negative sign at the last minute. Oops, but so I could still get the right answer, okay? So we got 7 kilograms at, oh, now, see, we know what the acceleration is because we already solved that from before. So I can pop that in right there. And algebra rearrange, get that, okay? Notice 17.5 newtons. That's smaller than 70 newtons. And it's also larger than 10 newtons, right? Exactly as it should be. Right? The theoretical maximum tension this could go, it could approach 20 newtons. It could be up to twice as big as the small weight, right? Like if you got 21 newtons, I know that would be wrong because it could never be over 20. Right? If this was like a big old weight and this is like a little dust particle, then this could go up to 20. Or it could go up to twice the weight of the dust particle. All right, so you guys go with the Atwood. Go with the Atwood. All right, let's see what we got next. Got this modified Atwood. Right. Right. If I didn't have any of the free body diagram forces, could you guys draw that whole free body diagram from scratch? You guys good? So see, the hang block provides a weight. Right? Now that might be the only external force driving the system, possibly. Right? I see the tension is just internal to the system, right? So probably ignore that unless you're asked about the tension, right? Now the top block also has a weight, but it's canceled out by the normal force as long as it's a level surface, right? And there may or may not be a friction force. A lot more often than not, they like to get rid of the friction, right? But they could throw it in there, right? That's it. Right? So a little bit different way you work that out. It starts with Newton's second law of motion, right? In this case, again, usually the hanging weight is the only force driving system, right? But if there's that friction right there, you have to subtract. This is whole system's point of view. There's the total mass being moved, right? You can do the same thing as we did before to figure out what is the tension. Right? Notice for the hanging one, it's weight down, tension up is equal to ma. Right? For the one on the surface, it might be that the tension is the net force, right? But if there's friction, then you have to subtract that. And that's what I did right here. Right? So if there's no friction, just only the tension provides the mass times acceleration of the top bar. Right? If you have like little wheels like you guys did for your version of that, you do that. All right. They got next. Ooh, Hooke's law. Hooke's law. I think you guys are pretty good at this. Have a graph, have an equation. Right. You guys write down some stuff about Hooke's law. What's the graph? What's the equation? Right. Did you guys come up with that right there? Right. F equals kx. Right. F equals kx, and then the graph is usually like f versus x, and then it's a straight line. So the slope represents the, guys, what does the slope of that line represent? The spring constant k. It's like F equals kx, right? And ooh, it looks like I'm starting to shade in a green triangle. Guys, what does the green triangle represent? Or should say the area of that triangle. The area under the curve. Yeah, so you could say work done to compress or stretch the spring, right? Which would also be equivalent to the spring energy stored. And so the elastic spring potential energy, right? And guys, what's the formula for elastic spring potential energy? 1/2 kx squared, right? There you go. Right? So I know that's all in terms of variables, but you can attach numbers to that, and that would always be valid. So you got forces kx, got energies 1/2 kx squared for spring. Right? You guys got that? And your notes. Let's do this. We're going to pull a block horizontally at constant velocity. So, of course, I got it covered up, but say I have a horizontal table, say I attach a spring scale to that block and then pulling it at constant velocity, okay, across a horizontal table. What does the free body diagram look like? for that scenario. Pull a block horizontally at constant velocity. Walk around, so you got this. Okay? You guys remember to also label all your force vectors too, right? Okay. Yeah, that looks right. So, right, so when you're drawing arrows for your vectors, right? So, see, so the block pulls horizontally at constant velocity. So you're pulling the block horizontally across the horizontal table at constant velocity. Okay. Okay. All right. Yeah, okay. I think it looks pretty good there. Right. So remember, if this is a free response question, don't just draw arrows. Also label what are those arrows. Okay. So here's what I came up with. Right. So this block has a weight and a normal force that balance out. So label it weight, normal force, boom, boom. Okay. I'm pulling, so usually applied force, you can call it spring force, okay? And if I only had those three, would it be going constant velocity? No, because there would be a net force. Right? So in this case, there has to be friction, doesn't there? Right? Like this wouldn't work on an air hockey table. Right? Or if it was an air hockey table, you could set the puck in motion and then you wouldn't be pulling at all. Right? You would just be letting it go. Right? But if you want both of these conditions, pull and also constant velocity, then there has to be, in this case, friction. Okay. I've got a challenge for you guys. Okay, car brakes to a stop. Okay. Suppose there's some known coefficient of friction between the tires on the road. Right? We'll call it mu, but it might have a value like 0.8 or something like that. Right? Let's say friction force could be 80% of the normal force. Right? But in general, it could be mu. Who could tell me what is the acceleration in that car? So the car's driving to the right, but slamming on the brake. So when I say acceleration, I really mean like slowing down. Right? Sometimes you hear the phrase deceleration, but don't write on an FRQ. Don't write the word deceleration. Okay? You can say negative acceleration or something. Okay? What's the rate that car's slowing down? In terms of, here, I'll give you guys a hint. In terms of coefficient of friction and also the gravity field ends up being important. If you played this out on Mars, it would work differently because there'd be a different gravity field. Okay? Right, this one's a little tricky. Ooh, I'm really curious who's actually going to get this one. Right? No, just the acceleration. Right? What's the rate the car is slowing down? So you're in that car, you're slamming on the brake, right? and you can feel slowing down. Like you feel like you're thrown forward relative to the car because of inertia, of course. So what's the rate the car is slowing down? And you can find the answer in terms of the coefficient of friction between the tires and the road, and also the gravity field of the planet. And then run it in here and MTX. Got it. All right. All right. Yeah. Or yeah, okay, yep. Got a winner here. All right. Think Addy got it, Max got it, Steven got it. All right, all right. Yeah, you guys are getting this. You guys are getting this. Okay. So how did I do it on this paper? Said okay. It's going to play into second law of motion at some point. Right? So throw that on the board. Right? If you're not sure, like if you get this as a free response question, like, oh man, I know we just looked at that 9 days ago. Right? At least throw down what you know, because that might be a point. This is a free response question. Like boom, point. Right? Got Newton's second law of motion. Okay? Guys, what is the net force? Oops, I meant to reveal that B, but of course you guys don't draw that on free body diagram. Okay. Guys, what is the net force on that car? So which force? The friction. Right? Because the verticals cancel. The friction force is the net force, isn't it? Okay. Oh, and what is friction in terms of the normal force? Yeah, coefficient of friction times normal force. Right? Oh, and as long as you have a level road, what is the normal force equivalent to? The weight. Right? Mg, the weight. Right? And then Hey, does the mass of the car cancel out both sides? Right? Guys, this is a really classic physics question, especially that detail I just mentioned, the mass cancels out. Right? So if you have a small car versus a large truck, and they have the same tires and they drive on the same road, right? Say they even start at the same speed, right? They got to break the same distance, right? Because the mass cancels out. That's a really classic physics scenario. Right? How about air hockey puck at constant velocity across a level air hockey table? What does the free body diagram look like? Um, do, would the air hockey puck have a weight and maybe a force from the jets? That's kind of like the normal force, but I guess it would just be force from the jets, right? Something like that. Right? Now, if it's sliding across the table at constant velocity, are there any horizontal forces? No. Right? Now, maybe just to get it going, you had to tap it with the to get it going, right? But once it's already going, yeah, notice there's no horizontal forces, right? If you drew that free body diagram, you wouldn't even draw this V here because that's not part of the diagram, right? I'm just putting there for context. Right, that's good. How about, let's go back to the cliff. Now let's get a velocity versus time graph going. See V versus T, velocity versus time. Okay? Let's consider air drag. If AP asks you to do that, they might ask you this, maybe. I doubt it, but it could. Right? What would that graph look like? Maybe this could be a multiple choice question, right? And they might give you multiple choice answers. Right? What is all right? So go to the edge of a very tall cliff, right? Drop an object, falls down, right? And it's facing air drag. Let's say significant air drag. Aha! Yeah, velocity versus time. Here's a hint. What if there was no air drag? What would that graph look like? It would be linear, wouldn't it? Right? So maybe I'll start off that way. It could be linear. And then say, okay, well, now I'm going to introduce air drag. Because now if there is air drag, it probably doesn't really affect it a whole lot for the first few meters of fall, first maybe a couple seconds. Okay? But after a while, it's eventually going to reach what kind of velocity? Terminal velocity. Okay? I'm thinking something like that. Okay? Yep, it starts off linear, and the slope would be the gravity field. Okay? But it's eventually going to asymptotically approach that terminal velocity, isn't it? Okay? The math to solve that is I saw this solved once. It was in a class called differential equations, which was a post calculus 3 class, and yeah, so we're just gonna leave that at that. All right. Suppose something's hanging in. Oh, whoops! I guess I got the here. Oh, this is okay. Hanging in equilibrium from a spring scale. So weight down, spring force up, balance out, zero out. Right. Oh, guys, that could be a different question from what if you start with an unstretched spring and you put an object on, let's say I put this on it, right, and then I drop it and it overshoots the equilibrium position and goes to some maximum stretch. That is not what this is, right? This is maybe if you carefully lower it to equilibrium, or if it's been oscillating for a few minutes and then eventually comes to rest, that's what this is, right? This is equilibrium, right? That's where the forces are balanced. It could be at rest, maybe, right? That's what that is. Right? Mg equals kx. Here's give it. Okay. Ooh, it's block on a incline time. Block on an incline. Look at this title: zero friction incline. Hey guys, if there's zero friction, there's no coefficient of friction, right? Because coefficient of friction would just be zero. Okay? What I want to know, you guys know what I've got covered up. The picture is a block on an incline, right? Block on an incline. Right? What does the free body diagram look like first? And the follow-up question is, what is the acceleration as a function of gravity field and the angle that it's ramped up from the horizontal? So 2 questions. First of all, what is the free body diagram? Yep, free body diagram, got it. Yep, got it. All right, so you guys get this free body diagram. Right. Once you got the free body diagram, go ahead and answer the second question, which is, what is the acceleration? What is the acceleration? Yep, got the free body diagram. Got it. All right, thanks. Some of you guys are getting there. Right. So this could be an air hockey table. There's definitely no friction. Yep, got the free body diagram. Right. Yeah, so now can you figure out what is the acceleration? Oh, do you guys think the mass of the block is going to cancel out to get acceleration? Yeah, to get acceleration, that would be true, right? But I bet the gravity field of the planet matters. Play out differently on the moon. I bet the angle of incline matters, right? Because if it was a flat table, there would be no acceleration. Okay. Right. So, yes, so zero friction, right? Zero friction. All right. So almost everybody got the free body diagram at this point. Yes, there's only two vectors. Right? So just draw the weight down and label it weight, and draw the normal force off at some angle. Notice it's not straight up. The normal force is not straight up. The normal force is perpendicular to the surface. Okay. It's got that. Okay. Now, I threw in some extra details. So I broke the weight into components, but notice I dashed the components. Right? If you draw them at all, then make sure you dash them. Right? Right? That angle's that angle. That's a match. Right? This block might be sliding, maybe, or maybe it starts from rest. Right? Made that ambiguous. But guys, you guys going to draw velocity vectors on a free body diagram? No. Right? So those are separate. Those are just. Right? Right. So let's see, we're trying to figure out what is the acceleration. Hey, do you think this is going to play into Newton's second law of motion? Right? Guys, if you're ever asked acceleration, you're going to answer that from one or two perspectives. It could be kinematic, like, oh, there's a cliff that's so high, it takes so much time to reach the bottom. That's a kinematic approach. Right? The other way is forces and masses. Right? So hey, that is my first step. Newton's second law of motion. I wasn't sure if it was or not, but yeah, Newton's second law. So, but that could be a point. This is a free response question. Okay. Guys, what is the net force on that block? mg sine theta. It's this component right here. mg sine theta. That feeds in right there, doesn't it? Point. Mass cancel. There you go. Okay. G sine theta. Okay. In fact, if this was a multiple choice question, I think this might be another good expression to pull from your back pocket. So like, boom, solve it real fast. Done. Right. Of course, if it was a free response question, you want to show all the steps. Okay. Got that? All right. How about let's go block an equilibrium on incline. Okay. Block equilibrium on incline. Okay. I'm gonna walk around and see who gets this whole thing. Now, equilibrium. There's a little bit more to this free body diagram. Who's gonna get this exactly right? So there's block on an incline, it's in equilibrium. Okay. I want to see the free body diagram. Who's gonna get the full free body diagram? All right, got Steven got it. Max got it. All right, almost. Who's gonna get this? All right, Steve got it. Addie got it. Catherine got it. Right. Ooh, almost. Okay.
Oh, shoot.
Almost. All right. And some of you guys are real close. We got 1 minute left. 1 minute left. Okay, here we go. Here's the answer. All right, guys, you guys got to know this one. Guys, does the Earth pull the weight straight down?
Yes.
So weight straight down. Now I can break that into components. Right. The normal force, a bunch of guys got correct, is perpendicular to the surface. Right. And there has to be a friction force in this case because equilibrium means zero net force. Right. So okay, you guys got that? All right, that's our pause point today. All right, you guys have a good day. See you tomorrow.